Alright, so are we back? Hopefully so. Let me see here. Welcome. Hello, hello. So here we are. Let's go ahead and keep solving some problems. This time around, factor combinations. Let's see if we can solve this one a little faster. The last problem I spent about an hour on. Let's see if we can go faster. Let's see how fast we do, how quickly. Numbers can be regarded as product of its factors. For example, 2 by 2 by 2 is 8, 2 by 4 is also 8. Write a function that takes an integer n and return all possible combinations of its factors. You may assume that n is always positive. Factors should be greater than 1 and less than n. Excuse me. Oh boy. For 1, no factors, 37. No factors, 12, 2 and 6, 2, 2 and 3, 3 and 4. Put 32, 2 and 16, 2, 2 and 8, 2, 2, 2 and 4, 2, 2, 2, 2 and 2, 2, 4 and 4, 4 and 8. Oh no. Well, this is a hard question. This is an interesting question. Basically, it boils down to, yeah, this is tricky. Not hard, but it's a tricky one. Doing it efficiently is also really tricky. So, first things first. Factorizing, just finding the prime factors of a number in the first place is challenging. It's very challenging. Yeah, prime factorization is a challenging thing just to begin with. So I don't expect there to be a particularly efficient algorithm for this. Like, I don't know what numbers they're going to give us, but excuse me. I'm assuming the number n is relatively small. This gets very hard depending on how large the value of n is. So pretty much for each divisor of n, and there's square root of n pairs of these divisors, for each divisor of n that you could have, you can recurse and combine for all the different ways you can set up the factors for n. So as an example, take 32, right? And you say, okay, there's a few different divisors. 2, 3 doesn't divide, 32, 4 and 8. 5, 6, 7, 8, I think. But the square root of 32 is only 5. Yeah, so it's actually done right here, right? 2, 4, 16, and 8. And what you do is you say, okay, take 2 and 16, take 4 and 8, recurse on 16, recurse on 8. For 16 you get 2, right? Square root of 16 is 4. 2 and 8, 4 and 4, right? 8 we said, and obviously we can memorize the solutions as well, so it's slightly more efficient. The square root of 8 is, I think it's like less than 3, right? It's got to be less than 3. So 2 and 4, and then obviously 3, that's really, it's just 2 and 4, right? So you would take all the solutions for 18 and you would basically append 2 to the front, or append those solutions to 16 onto a vector containing 2. And you're not really done yet though for 16, right? Because 16 then goes to 2 and the solutions for 8, and then 4 and the solutions for 4. And the solutions for 8 are 2 and 4 also, right? Which, this is just 2 and 2. So 8 you get so 8 you get 2, 4 as well as 2, 2, 2, right? Obviously the number itself counts. So there's a helper here. It's not quite the recursion exactly. The helper recursion is useful because the number itself is not going to be returned. But in these recursions, the number itself does get returned as a possibility. So here you go. For 8, you get 2, 4, and 2, 2, 2. And so for 16, you get 2, 2, 4, 2, 2, 2, 2. And then 4 and 4 is, we said 4 is 2, 2. 4 is 4 and 2, 2. And then finally, 16 we said is, so so it gets a little confusing, but so we have 16 and we have 8. 8 is 2, 2, 2, and 2, 4, and 2. Yeah, we'll just, 2, 2, 2, and 2, 4. And 16 is 2, 2, 2, 2, 2, 2, 4. That's 8. That's 2 of these, right? And then 4, 2, 2, and 4, 4. And then we said 2 in front of 16. So all of these, and 4 in front of 8, for all of these. So 32 gives you 1, 2, 3, 4, 5. And then these can be boiled down to, you remove all the duplicates. Plus these other ones, 2, 16, and 4, 8. Yeah. Something like this. You get 5 for 32. I missed one. 2, 2, 8. Right. Yeah, I missed that 2 and 8 for 16. I know I missed that. Yeah, 2 and 8 and 4, 4, right? So it gets a little funky, but But that's pretty much it. Yeah, you want to use sets, so that way you would remove any duplicates, and then you just dump all these sets into a vector. A set of sets, we'll say. Yeah. Can you do a set of sets? I don't know if that works. Let's see. What happens here? Yeah, okay, it works. It'll remove the duplicate sets. So, let's try this. Say retrieve divisors of x. So for int I start at square root. If x modulo I equals 0, then we have a divisor. And now we say for divisor, for each divisor, you're going to and we have memoize too. Memoization as well. Okay. Okay, so this is kind of funky, but what you're going to do is for each divisor, you're going to add your new set, that divisor, and then you're going to take f of x divided by d, and that returns a set of sets. And for each set in that set of sets, you're going to you actually do it the other way around. You do it. You create this new set. Insert D. You do it this way. Really, it's done this way. Now, here's a tricky thing. It's actually a set of vectors. If you do a set of sets, the problem with a set of sets is that you can't have duplicates in the set. So 2, 2, 2, 2 is not going to work. No, that's a mistake. So actually, we can't just use sets to get rid of duplicates. Can we do sets of vectors? Hold on. Oops. Alright, what do we get here if we do this? Oh, I thought I was missing something here. It wasn't here though, it was there. Okay, so you can do this, it's just oh, no. Oh, yeah. You can do this. Yeah. Okay. All right. We're okay. We're fine. We're just a little uncertain. We have to just sort our vectors. That's all. Okay. Something like this. Yeah. Yeah. So for each divisor, you're going to take f of x divided by that divisor. And you get this vector, which is a copy of s, which is really just a v. We'll call it new v, I guess. And then we push back into new v, and we sort that new vector, and then we insert that new vector into a return set. Right, and then we return that ret at the end here. And this is going to be a set of vectors of integers. And there's one thing here, tricky thing here, which is we could probably do this in one. We probably don't need to break this up into two pieces. I could probably just, make this loop here, put that loop here. Combine these two loops. But also, something to consider is this should contain this vector should be in this set as well before you return. Yeah. It's a tricky thing, but I just want to see if this compiles. Before we combine this with this, I just want to see, so we recurse. Don't really need that anymore, do we? Whoops. Okay. All right, now. So this is going to be for each set. It really could just be just say for yeah, that should be fine. What does this look like if we do this? Right, I thought maybe there was some error there. Oh. Okay. What? No matching call? Huh? Oh. Gotcha. Forgot. Okay, it compiles, it seems to work. So if we do 10, what do we get? Two, 5, 10. Oh yeah. Okay, looks like it works. Looks like it even works. Amazing. Amazing. And so what we do is auto result equals recurse of n recurse, and then we say result dot remove or delete erase. And you just remove that one value at the end. And that should be it. Oh, okay. Let's see if that works. There we go. Um, 100, 32, 37, 12. Let's go. Let's see what we do. Got him. All right, great. The one thing we need now is we can do this. Oops. For DN divisors, and we just say don't need these divisors anymore. Can just say, put that if statement right there. And recurse on them. Right. So yeah. Okay. I think we just go for it. Yeah, because it's not going to be efficient no matter what, this approach. Oh, that's interesting. Okay. Hey, okay, it's cool. Yeah, like I said, doesn't have to be efficient, but kind of awkward. Kind of awkward. A little awkward, I'll say. Definitely peg that as rather awkward. Uses a bit of memory. Uses recursion. Uses sets to remove duplicates. Pretty inefficient thing, though. Pretty inefficient algorithm. It'll always be inefficient, though. That's the thing. Is like I just happen to know that factorizing numbers is just naturally inefficient, so that's got to be just inefficient. So, sweet, done. Very good. On to the next thing here. On to the next thing here. So we'll go ahead and end stream here, and say thank you for watching, those of you that did. See how long did that take? Yeah, half an hour. Okay, I mean, it's kind of a good amount of time, a fair amount of time. Yeah, let's stop